going to do is tell you what was going on today. We are going to be covering today this section. Straight off the top, this question is basically how do you use calculus to help you sketch curves? More than half of what's in here, you actually know how to do from other things. You've sketched functions, especially polynomial and rational and trig functions. You've already sketched those guys in 141 and 142. So really the only extra here is that we're going to be doing local max and min using first derivatives, and to a much lesser extent points of inflection using second derivatives. The second thing is that this particular kind of question will not be happening in the test on Monday, test 5. And this particular kind of question will not be happening in the final exam either. And mostly because they take far too long. And it's not that they're difficult to do. In fact, pretty much everything that's going to be done here, you've already done somewhere else. So I can test that you know how to do it. So we're going to look at how do you sketch polynomial functions, which are the first 3 in the homework. How to do rational functions, that's the next 2. How to do a trig function, which is question 6 essentially, and any other function, that's the last 2. So get straight in with the first one. I'm going to do actually question 2. And we're being asked to sketch 8x cubed, take away 48x squared plus 72x. And if I wanted to sketch this in Math 141, I would find the x-intercepts and the y-intercepts. So let's do that. Let's get the x-intercepts. Well, the best way to find x-intercepts of a polynomial is to factor the heck out of it. So anybody want to tell me a common factor that I could use on this guy?
8x.
8x.
Agreed. And if I did that, it leaves me with an x squared, take away a 6x plus a 9. And this quadratic factors as well. So in this case, it ends up being that guy, which in turn becomes that guy. So I haven't done any calculus right now. All I've done is factor the heck out of it, essentially style points. That gives me 2 and only 2 x-intercepts. Are we all comfortable about how you find x-intercepts from this? Because what you do is essentially solve for when it's 0. Right? Now, if I want to get a y-intercept, they're much easier to do. You just evaluate the function at 0. Can you just trust me that the answer is 0? So right now, I have a couple of places of interest, and I'm going to put them here. So as I find things, I'll put them in here. It has an x-intercept at 0. And it has an x-intercept at 3. And it has a y-intercept at 0, which I've already got because it's the origin. And that's us done. Those 2. Vertical asymptotes and horizontal asymptotes. Well, would you agree that this shape doesn't have any? So I'm just skipping by that. There's no vertical asymptotes and there is no horizontal asymptotes because I can tell looking that there isn't. And now I'll move on to step 5. And step 5 is local max, local mins, using derivatives, right, to find them. We've done that. Isn't that all about increasing, decreasing, local max, local min, right? So I'm going to start with my function again. Only I'm returning back to the untouched version and differentiating it. And that gives me 24x squared 96x plus 72. And I should be able to pull out 24, I believe, as a common factor. Are you happy about the differentiation and the factoring of the answer? When good? If I make a mistake, you tell me now. So, moving on then. I need to find critical numbers. That is places where the derivative is 0. Would you agree that this function doesn't have any undefined values? So I don't need to look for those. And so I'm going to have to solve when this fella is 0, which is at x equals 1 and at x equals 3. And we've been doing that for a while, haven't we? Isn't there a whole section devoted to finding things like this? Now, what we're going to do is create our number line for the derivative. And on this number line, I'm going to put that when x is 1, the derivative is 0, and that when x is 3, the derivative is 0. And then I would choose test points. And you're just going to trust me here because we have a time crunch. I'm picking 0, and I plug it in here, and the answer is positive. And I plug in 2, and the answer is negative. And I plug in 4, and the answer is positive. And now I can look at what's going on at the values of 1 and 3. At x equals 1, it's positive, 0, and negative. So that means there is a local maximum, and it's at point 1, comma, and I just go back here and I plug in 1. And goodness gracious me, what on earth is the answer when you get 1? 72 take away 48, add to 80, 32. Okay, at 1 comma 32, there's a local max. Fair enough. At 3, it is negative 0 to positive, and we call that a local min. And that's going to be at 3 comma, no idea, but here it goes, 8 times 3 cubed. Take away 48 times 3 squared. Add 72 times 3. I don't know why I bothered to do that. I should have known the answer was 0 anyway, because is it not on the x-intercept? So what does my picture begin to look like now? Well, at the point 1 comma 32, 5, 10, 15, 20, 25, 30, 35, somewhere about here, there is a local max, something like this. At 3 comma 0, there is a local min. Would you agree that this piece here has to join up with that piece there? And that this guy just keeps going onwards, and this piece here goes down really steeply. So it's got a bend in it. It's probably not got a bend in it, but yeah. You can tell I'm not very good at being an artist, but isn't that the gist of the shape? Now, technically speaking, well, there is one last thing that we do, and that is that we use the second derivative define concave up, concave down, and in particular points of inflection. So I will do that. We have a first derivative that looks like this. The second derivative is 48x take away 96. We're trying to solve when is it 0, right? Because that's the critical numbers. And when I solve this fella, can you take it from me that x equals 2? I'll draw my number line, which is a much smaller version, second derivative. There's x equals 2, there's 1, there's 3. The second derivative is 0 here. You do a test point of 1, it's negative. You do a test point, it's positive. Doesn't this mean at x equals 2, there is a point of inflection and it's concave down, you know, on this side, and it's concave up on this side, right? So concave down means it looks like this, concave up means it looks like this. Well, you're not telling me something I don't already know. I mean, the only thing I really get out of this is that at 2 comma somebody, there is a point of inflection. So I've lost my, oh, it's up here. So 8 times 2 cubed, take away 48 times 2 squared, plus 72 times 2. And the answer I get is 16. That's actually pretty good. That would be about there, because that's 15. And that's there. Yeah, that's pretty close. And would you agree that the second derivative didn't really bring that much to the party? You kind of knew most of what you needed before then. And that is how you use calculus to help you sketch a polynomial. Really, what calculus allowed us to do was to find these two guys right now. So, next guy is going to be a rational function. And the guy I'm going to pick, the rational function one, is this one. Question 4. So we're going to sketch a fraction function. And I'm going to pull out a common factor of x, and I'm going to factor the bottom. And so before I do anything involving sketching this guy, I've already factored it. And it's always a good idea for rational functions to do this, because now and again, it doesn't happen a lot, but in this case it does happen. Something interesting happens. Can you see any cancelling? No? Can you see something on the top cancelling something on the bottom? I can.
Would it be negative x over x minus 6?
Nope, that's not allowed, Isaac. But keep thinking, what could be allowed there? Something on the top is cancelling something on the bottom. And these two are not going to do it. Michelle, you were nodding. Thank you. X minus 1. And it cancels with 1 minus x. And somewhere in your Math 99 life, you were told that you're allowed to cancel a minus b with b minus a. But when you did cancel them, what gets left behind?
-1.
Minus 1.
I think that's what The person who talked before was trying to say.
Oh, well, then he is, Isaac, you are totally correct. If that's what you're trying to say, I just didn't hear it that way. So that was my fault.
It's okay.
Is that what you were trying to tell me?
Yeah.
Oh, God, no. I thought you were trying to tell me that this cancelled that. What you were trying to tell me is this was what would be left after you cancelled, right?
Yeah.
I gotcha. Yeah. So you were thoroughly confused when I said, nope, not allowed. But now we've met up and it's okay. What that means is that don't I have a much simpler function to sketch? I've also taken care of the fact that I might accidentally think that there's some phantom x-intercepts that are not really there. But there is one thing I have to take care of. At x equals 1, because I've removed that from this question. Make a hole in your function at x equals 1. Just a little circle saying at x equals 1, the function's undefined. Right, now, from this function, I can get its x-intercept. What makes that 0? X equals 0. I can get its y-intercept. Its y-intercept is also 0. So basically, it crosses the origin. That's all I know. Now, this shape has a vertical asymptote, doesn't it? Where is the vertical asymptote for this function?
Six.
Okay. And it's at x equals 6, you're right. So let's start putting some of the puzzle together. It's basically like a jigsaw, and hopefully all the pieces will fit when we're finished. Well, I know that it passes through the x and the y axis at 0, right? So that's that guy. And 1, 2, 3, 4, 6. And at x equals 6. Very unvertical looking line. We have our vertical asymptote. Okay. This particular function, right? This is the one we're looking at. Has a horizontal asymptote as well. Does anyone know the equation of the horizontal asymptote for this guy? It's a 141 thing.
Sorry, I didn't hear that. Can you say that again?
What is the equation of the horizontal asymptote of this rational function? It's a while ago, isn't it? 141. But, okay. This is how you can do it now. A horizontal asymptote is the limit of a function as x tends to infinity and negative infinity as well. And in this case, we are trying to find the limit as x tends to infinity of a fraction. Wait a minute, isn't that L'Hopital can do that because this is indeterminate form. And so it becomes the limit as x tends to infinity. If you differentiate the top and the bottom, you get the answer, -1. So y equals -1, which is here. So there is a horizontal asymptote at y equals 1. Oops, -1. So we know it passes through the origin. It has a vertical asymptote at x equals 6, and it has a horizontal asymptote at y equals -1. Right now, in calculus, we use L'Hopital's rule to find that. You could have just found it by you know, divide top and bottom by x and get -1 that way. You could have done it by long division, which is pretty much how you would have tried to have done it in 151. Now, regardless of how you do it, that's the answer. So we're now moving on to calculus. Our function. So we're going to go hunting for max and min, increasing, decreasing, all that good stuff. So I'm going to find its first derivative. I'm going to call this f. I'm going to call this guy g. So this is going to be a quotient rule. Differentiate the top, you get -1. Leave the bottom alone. Take away. Leave the top alone. Differentiate the bottom. And the whole thing gives you that. Distribute, you get -x, add 6, add an x. We are now left with a first derivative that looks like that. Now, I need to find critical numbers. For this fraction, is there any value of x that would make this fraction 0? Well, you only need to look at the top. Would you agree there's nobody? Right? There are no places where the derivative is 0. What does that tell me? It tells me that this shape does not have any local max or mins. It has no hills, no valleys, right? It's impossible for that to happen. Okay. But it still has a different kind of critical number, because aren't critical numbers also places where the function is undefined? What value of x is this fraction undefined?
1.
Not number 1. What value of x would make this not 1? What would make this a bad number?
6.
Yeah, right. Make it 0 in the bottom, right? 6. So we have an x equals 6, and that's the guy I am going to be doing my number line of the first derivative. So there's 6, make that 7, make that 5, so on. And then here, the derivative is undefined. And then I choose test points. And if I pick a number on this side, like 5, the derivative ends up being positive. And if I choose a number like 7, it ends up being positive. And then we have to try and figure out what's this telling us that will help us sketch it. Right. At x equals 6, I have a vertical asymptote. On this side, the slope is positive. That means it's going uphill. So you are telling me essentially that it's going uphill, right? You agree it's positive slope. Now, on the right-hand side, right, that's on this side, it's also positive. So you're telling me that the curve is pointing up the way, right? Well, would you agree it's pointing up the way? Actually, it's also got the ladder there. But I'm pretty much ready to do this yet. Would you agree that in this case, it levels off and then it levels off? Now, I haven't used the second derivative, and that's for time purposes. But can you trust me that if you did the second derivative, it would tell you pretty much nothing useful? There aren't any places where the second derivative is 0, and the only undefined value is a guy you already know about, which is 6. and it still tells me the curvature which I already knew. So I didn't get anything out of the second derivative, so I'm not going to spend any time doing that now. Are we good on that one? Any questions about the process? Going to do a trig one, question 6. Basically, we're going to do 4 questions, and I want to show you some information that I have in Canvas. And in question 6, why am I only going to sketch this guy in the range 0 to 2 pi? Give me a practical reason for why it just makes sense to do that.
It goes on forever.
Yeah. So if I find out what this looks like, couldn't I just say that's the basic shape and just keep repeating it? You know, the next 2 pi, repeat the same shape, the next 2 pi, and so on forever. So that's a good idea. When you do a trig function, to just restrict yourself, you normally get a better idea of what's going on. Right, now, I have my little hit list, x-intercept. This guy, right, I solve it for when it's 0. So when is this guy equal to 0? Well, he's equal to 0 when the sine of x is 0, which means at 0, at pi, and at 2 pi. Second guy, that's the x-intercept. Let's do the y-intercept. Well, you find the value at 0, and you get 0. So that's basically the origin. Start putting some pieces together. Here's 0, pi, 2 pi. And I know that it passes through the origin. I believe it passes through pi, and it passes through 2 pi. And you might think, why didn't I put pi in? Well, you're going to find out in a few moments why I didn't do pi. Let's find vertical asymptotes. Doing pages all over the place. Right. 3. This shape has a vertical asymptote, as all shapes that have them, only when the bottom is 0. Right? So if you have a rational function and the bottom is 0, you're probably going to end up with a vertical asymptote. Probably. Which means, what value of x has a cosine that's equal to -1?
Wait, oh, pi.
It's pi. Now, if I return back to, oh, there's an x-intercept at 0, there's an x-intercept at pi, and there's an x-intercept at 2 pi, but isn't there also a vertical asymptote at pi? Now, you can't have an x-intercept and a vertical asymptote at the same place. Which one of those two will always win? If you have a choice between an x-intercept and a vertical asymptote, which will you expect to be the thing that's really there?
Asymptote.
Yeah. That's why this guy was not put in as an x-intercept, because a vertical asymptote trumps an x-intercept, right? So, well, we got a bit of a start, right? We got some stuff. We got lots more to find. This shape Does this shape have a horizontal asymptote? Correct. Sabina is shaking her head. Do you want to tell people why you know that? Because it is correct.
I was going on gut feeling. Actually, I hadn't mathed it out yet.
Yeah. Well, gut feelings are good. Don't trig functions tend to repeat themselves. And you can't level off if you repeat yourself, right? So it's a kind of, yeah, it's a kind of gut feeling anyway, right? So it has horizontal asymptotes. It has none. Now let's move to the next phase. And the next phase is that we need to find local max and min and all that good stuff. So here's the function. I'm going to find its derivative. Top will be f, the bottom is g. So this is going to be a quotient, no? Differentiate that guy, you get cosine x. Leave this guy alone. Take away. Leave this guy alone. Differentiate that guy. All over this guy squared. Cosine x plus cosine squared x. Two negatives make it a positive sine squared x. All over 1 plus cosine x squared. Is there any trig identity that you can see to make this pretty? Because we're on style point mode now.
The cosine squared and the sine squared just make 1.
So I now have cosine x plus 1. And something remarkably rare has happened. This is not typical, but it has happened here. Can you see anything interesting?
The top and bottom are like negative, so you could wait. I mean, no, they're the same, so you can.
Yeah. So I can cancel one, couldn't I? Isn't the top basically 1 plus cosine x? Can't it cancel out one of these? And it's almost like, wow, how did that happen? But doesn't wow things happen with trig? Because trig identities do weird stuff. So that derivative is actually quite nice, isn't it? Quite simple. Does this shape, because this is its derivative, does this shape have any zero derivatives? So no max and mins again. Agreed? No maximums or min. Does it have an undefined? Right? Well, this, right, so y dash equals 0, none. But what about y dashed undefined?
Yeah.
Well, yeah.
Yep.
Where will that happen?
At cosine x is pi. It's
Okay.
-1.
Oh, wait a minute. Don't we know about that guy? Do you see that derivatives will find vertical asymptotes for you? Won't vertical asymptotes be undefined derivatives, right? Places where the derivative is vertical, essentially. So I am now going to use the fact that we know the derivative, and we know that there is one particular guy at pi. And at this fella here, the second derivative, I'm sorry, the first derivative is 0. If I pick a number like half pi as my test point, it's positive. And this guy is my test point, oh, it's also positive. Then I should be able to go up here, and I should be able to figure out what on earth that is telling me. Well, it's telling me that if you choose a number like a half pi, the slope is positive, so it has to be going uphill. And if you choose somebody to the right over here, it also has to be positive, so it has to be going uphill. It has to get to here, and it has to get to here. Would you agree that the second derivative is really not going to tell me much, so I'll skip it? Actually, it's a pretty boring shape. If I imagine that this is at pi, and then you've got 2 pi here, and you've got 0 here. At 3 pi, there's going to be another one of these, right? And our shape looks something like this. Okay, that's what we've got. But if I duplicate it, do you see what it's going to look like? Won't it look very like a tan function? You see, it looks very, tan function like. A pretty boring curve, but we sketched it, and that's what it is. Any questions? Last one. 7 or 8. I don't know which one I'm picking. Let's see. 7 is. So this is just one of many examples. This is just any other function in the universe. How can you use calculus to sketch it? So here's one. It's x-intercept. It's already factored. So all I need to do is solve for y equals 0. And only one answer comes out. It has an x-intercept at 1. Why isn't e to the x going to get me an x-intercept?
Because it never equals 0.
Because it never equals 0. Exactly. Number 2. We're now going to get the y-intercept. And the y-intercept is basically the value of the function at 0. So it's 1 take away 0, e to the 0, which is 1 times 1, which is 1. So I now have an x and a y-intercept. And our x-intercept, is it 1? And our y-intercept is at 1. It's a start, right? After a little bit helps. Right, next thing in our list is, does this shape, and I guess it's kind of gut feeling because there's no way to prove it. Would you agree that this shape has no vertical asymptotes? Don't you kind of need, well, most of the time, don't you need a fraction to get a vertical asymptote unless you're a tan function, something like that. So vertical asymptotes, none. Now let's look for horizontal asymptotes. And I've already done this question with the previous class, so I missed this, but now I know I've missed it. I can check it out. Horizontal asymptotes happen when x is infinite and minus infinity. In other words, what does the curve do when x gets really big? This one here becomes the value as limit as x tends to negative infinity of 1 minus x e to the x. So far, so good? Now, you're going to say, and I hope at least you're thinking this, you cannot do L'Hopital's rule, unless you've got a fraction. Are you happy about how I turned this into a fraction? Isn't e to the x on the top the same as e to the negative x on the bottom? It's a little algebra trick, but we've done that before. Now, if you do L'Hopital on this, you differentiate the top, you get -1. You differentiate the bottom, you get that. Now I'm going to plug infinity, and actually negative infinity, into this expression. So it's going to be -1 over e of negative infinity. Now you've got to be careful here. Two negatives make a plus. That guy is now him, right? That guy is him. That guy. Oh, shit in space. It's negative x. Two negatives make that a plus. It's negative x. The negative of negative infinity is plus infinity. I said be careful, and then I wasn't. Isn't 1 over e to the infinity 1 over infinity? The answer is 0. It has a horizontal asymptote of 0. I plugged negative infinity in here. E to the negative of negative infinity is e to the infinity, right? 1 over infinity is 0. What that tells me is that this shape, right? Excuse me. Has a horizontal asymptote here. If I did the other side, it shoots off to infinity, so I'm not going to do that. Moving on to our original function. I'm going to find its derivative. Call that f, call that g. We get f dash g plus f of g dashed. We get -1 times this guy plus this fella times e to the x. So that's this fella plus this fella minus that guy. And we get a very nice derivative. It's just that. When is this derivative 0?
0.
0. You're getting an abbreviated version of this now because of time. But if you do a test point on this side here it's negative, and on this side here it's positive. And what that tells me is that there's a local max. So it goes something like that. Okay, there are funny little kinks there because I can't draw well, but that's what you've got. So you basically got a shape that flatlines and does a bump. Only on this side it goes down forever. And on this side is horizontal. So that's the kind of basic shape. And the second derivative wouldn't tell me much. So it'll tell me a point of inflection, which I believe there's going to be one about here and another one about here. So for the last few minutes, I want to show you something new that is on Canvas. So while I'm getting this set up, you can say hi. And okay, where are you hiding? Yeah, okay, let's close that window off. Let's put that window on. Let's go away. Open that window. Looking good. Okay. Right, so you all set time by now? Looks like you have. Right. You should be looking at our screen, our Canvas page. Okay. Do you notice there's a new guy in town called Final Practice? Final Exam Practice. So, if you're wondering what does our final exam look like, this is an example of it. So, I'm giving you a really big version of it. So that's what it says right at the start. Your final exam isn't as big as this. Your final exam will actually only have 10 multiple choice. This has 22. And your section 2 will have 10 questions. I can't remember how many this has got, but it's no more than 10. And what it does is it kind of shows you how I ask questions and what multiple choice questions look like. So you get a question, but only one of them is true. And you pick, hopefully, the correct answer. And if you think there's 2 correct answers, you will pick the one that you think is right, because there's only one. Because in multiple choice, if you say it's A or it could be B, so you circle both, you will get 0 points. So you go A when that happens. And then you get section 2, and section 2 is full of all the calculus stuff. How many questions do I have? Just out of curiosity. Oh, I only did 14, so it's still bigger than the test, the final exam. Okay. So what's not going to be in your final exam? I will not be doing this graphing questions. Not because you can't, but they take too long. And all the bits that are in it, you could be asked anyway separately. Couldn't I just give you a function and say, find the local max and min, or find out when it's increasing or decreasing, right? I could ask you that piece of the puzzle, rather than the whole sketch it from start to finish. You will not be getting, remember those delta epsilon questions? And although you could be given, find the limit as, you know, of f dashed 1 from scratch, right? You know, the limit is h tends to 0 or x tends to 1. I will not give you the limit as x tends to a of x cubed, right? The generic one where there's no numbers.